Thank you very much. Okay, so I'd like to thank the organizers for giving me the chance to speak at this school. I want to thank the students also who have diligently shown up here despite the sunny afternoon. Very much appreciate it. It's good that there are no windows here. Like briefly introduced, I come from a slightly different field of physics. In fact, a completely, totally different one, but we use the same methods. Therefore, the reason for me being here. I've been working in integrability for quite a long time. In fact, you might not have had similar experiences to me, but I'll just share a couple of experiences with you. Essentially, when I was just a very, very young postdoc, I was insisting on trying to use integrability for real-world applications in condensed matter physics. I thought it would be interesting to try to calculate observable things with this, but that was of course very, very difficult. So most of the attention was focused on the theory itself, just bringing it up because of the hope that one day it would become useful. Of course, the beauty of integrability is a sufficient reason to study it. My experience back then was that, I remember having a particularly fistful discussion with a physicist at some point who was accusing me of doing the equivalent, the modern equivalent of counting angels on heads of pins. He said, you're just like a medieval philosopher. These people who gathered 60, 100 of them, who kind of wondered how many angels you could stack up in there. That's what you're doing. That's the kind of physics you're doing. You're saying you should do something useful. You should work on ITC. You should work on real phenomenology. Just do some real physics instead of just hand waving. Well, so it's a pleasure to say that 20 years after, I think this thought has been proven completely wrong. Because, as you're probably aware, integrable models have really come of age as far as experimental physicists are concerned. In fact, I remember when I realized that, it was at a conference in Paris where two cold atom experimentalists, one after the other, introduced the Young-Baxter relation. Then I thought, all right, so maybe times have changed. So there are many realizations now of integrable models in atomic physics and also in quantum magnetism. I will talk about that later on. Essentially, the plan that I have for the series of lectures is to first go through basics of integrability and then lead via the algebraic Bethe Ansatz up to the last session where I will talk about applications. Now, one of the great mysteries for me, of course, is the level of knowledge in the audience concerning various topics I'm going to plan talking about. So who in the audience has written down the coordinate Bethe Ansatz for the Lieb-Liniger model? That's good, okay. Who has studied thermodynamic Bethe Ansatz for the Lieb-Liniger model? Okay. Who has written down coordinate Bethe Ansatz for spin chains, Heisenberg spin chains? A few more. Okay, very good. So we'll go through that very, very quickly. And who has studied the algebraic Bethe Ansatz? Okay, that's good. Who knows Slavnov's theorem? Okay, very good. Okay, then there will be content for everybody in the lecture. Let me just outline my plan very, very quickly then, so I don't need to write it down really. So the first session was going to be a general overview of integrability for the Lieb-Liniger model. Talk to you about essentially everything you need to know for it. If possible, including thermodynamic limit, excitations around the ground state, and even thermodynamic equilibrium at finite temperatures. We'll see whether we finish that in the first hour. I doubt it. Probably going to spill over the second hour as well. Then I want to talk about the Bethe Ansatz also for the spin chains in the second session. Third session is going to be devoted to the algebraic Bethe Ansatz. I will explain to you the algebraic Bethe Ansatz like I like explaining it. And the fourth session is actually going to be a slide series of presentations giving you the modern applications of integrability and condensed matter. So that's when I'll really, really talk about dynamical correlation functions and these cold atomic gases and these spin chains. And I'll also present to you some absolutely brand new research that is going on in the field of out-of-equilibrium physics. I'll try to convince you that integrability is the appropriate tool to study out-of-equilibrium physics. Okay? I'll give you many motivations for that. If all goes well, you should have received a strangely folded and stapled series of notes. You've probably worked it out by now. What you need to do is fold them in two like this and remove the staple, and then you have a nice little book. Okay, I was very confused. I thought only half had been printed, but then we worked it out here. You know, a few professors of theoretical physics work these things out. So as I go along, I will only give you an extremely succinct summary of statements about these things, very often without proof, very often without derivation. You will find most of the derivations, proofs if needed, in the notes, which you'll be welcome to study in your own time. There's nothing more boring for a lecturer than to lecture uninterrupted for a full hour, or at least 51 minutes that I have left. So I welcome questions as we go along, irrespective of where we're sitting. Okay? Any questions? No. Okay. Right. So as was briefly said, essentially condensed matter is the setting where it all began, isn't it? So 1931, Hans Bethe publishes this wonderful little paper. He's like 25, 26 years of age at that point, so that should make you feel motivated. It's a very, very nice paper because, of course, it's the first of a series. If you look carefully at the title of the paper, it is number 1. And if you read carefully the last phrase of the conclusion, it says that in forthcoming work, we will generalize this to higher dimensional structures. Of course, the second paper was never published. Of course, there's a good reason for that. Bethe was not a cheater like Fermat. He didn't say, I know how to do it in 2D, but I will, I don't have space for this here. Bethe was an honest man, so he just never published number 2 because we don't know how to generalize this to higher dimensions. That's another funny anecdote. Actually, I had the chance 20 years ago to actually talk to Hans Bethe. I was visiting Cornell at that point as a prospective student, and then nobody went to see him, and I had just learned the Bethe Ansatz, so I knocked on his door and he said, come in, come in. And then we ended up chatting for the best part of an hour about his theories for neutrino oscillations and things. And then at the end, I asked him if he had one recommendation to give to a young theorist who wants to do well, what would it be? And then, of course, I was hoping that he would give me a half-completed manuscript, or preferably 99% completed manuscript, saying, just finish this off and you will be famous. But no, he just turned and he said, you have the back very, very hard. So that was a kind of live recommendation from Hans Bethe that I got back then. And you see why such a man was able to start the field of integrability, because it requires quite a lot of work. Okay? So with these motivational settings, let's just get started. Essentially, the whole first part of the course is going to be about the Lieb-Vinegar model. So let me just get this tablet to work, if possible. I'll have to put it in. Okay, so the Lieb-Vinegar model was essentially a model that was formulated before Lieb and Vinegar worked on it. Essentially, let's just write it down very quickly. Okay, so the model is a model for atoms propagating on a one-dimensional line. You can invoke periodic boundary conditions. We'll do that later. And essentially interacting with an ultra-local delta potential interaction. So if you write the Hamiltonian just in coordinate space, you would specialize and use the same notation that I use in the notes, be consistent. Okay, so let's just write it straight in first quantized version for n particles. This is just a Hamiltonian which is composed of 2 different terms. I'm going to put all annoying constants like h bar and the mass of particles to, well, h bar to 1, mass of the particles to 1/2 for convenience. So essentially there's a first dynamical term, which is just the free kinetic energy, which is just the second derivative with respect to the coordinate of the particle. But then there's an ultralocal interaction, which is pairwise delta function of these 2 positions here. Okay, so this is a relatively straightforward system to solve if you consider just 2 particles. This is just the kind of textbook problem of a single particle propagating on a line with a delta impurity somewhere. And you know, you remember how that goes. It's extremely elementary. So the delta function itself will induce a discontinuity in the first derivative of the wave function on both sides of this impurity here. Essentially, this is just a many-body generalization of it. In the notes, you're going to see essentially alternative treatment for an alternative treatment for interacting bosons in 1D. That's called Bogoliubov theory. It's not something that you standardly learn, but in condensed matter physics, it's a very important concept, Bogoliubov theory. So that's just explained in the notes. But essentially, what we can do here is something much better than Bogoliubov theory, which is an approximate approach working at small values of the interaction. Here we can just write down an exact wave function for this Hamiltonian. Okay? Now, I'm kind of tempted to just do that straight without derivation. I don't know if maybe I can try to do it or I'll go quickly in the lectures, and if you think it's too fast, then you just stop me. Okay? So the idea, of course, let me see which. Maybe I'll just do some general statements first. So this is a first quantized notation here. We can, of course, translate this problem in second quantized notation if you want. By introducing some vacuum 0 with operators these bosonic field operators, obeying the canonical commutation relations that we're used to, so you just have the commutator psi of x, psi dagger of y. Am I falling off the edge here almost? It's just some product of x minus y. And now, this first quantized problem here, if you write down the Schrödinger equation for this, it becomes equivalent to finding wave functions in second quantized notation that you would write in the following parameterization. You would have a quantum many-body state here that would carry n particles here. That would be the spatial integral of these coordinates with some amplitude now. Okay, that will depend on some rapidities that we will discuss later. In fact, let me just not even introduce that at the moment. Okay, so this is just some function taking a vector in the coordinate space of these n particles, and then I just have these creation operators. Acting on the vacuum. So, finding an eigenstate of the Hamiltonian in this first quantized notation is just completely equivalent to diagonalizing the second quantized Hamiltonian operator using this representation here. So if you want, this would become the first quantized version of this. I mean, you probably know this completely. So the eigenvalue problem that we'll want to solve in second quantized notation, it's just that we'll have the Blininger Hamiltonian. Acting on this is just giving us some energy with this state. Okay? And this second quantized version of the Hamiltonian here is the nonlinear Schrödinger operator that you've probably all written down very often. I guess have I even written it in the notes? Yes, so we just remember some H Schrödinger. Integral dx psi dagger of x dx psi of x plus c psi dagger square of x psi squared of x. Okay, so this is just the setting of our problem in second quantized notation. Okay. Now, the way you find the solution, like I said, is very much akin to the treatment of a single particle interacting with a localized delta impurity. Essentially, chapter 3 in the notes gives solution of the Schrödinger equation in terms of the Bethe Ansatz. Okay, so the Bethe Ansatz itself is a form of the wave function that contains a certain number of crucial pieces of information. Essentially, let me just write it down for you. It's an equation 3.22 in the notes. Okay, what this tells you is that the n-body wave function in coordinate space, it depends on a certain number of variables that are called the rapidities here. I guess you're familiar with that. So let me just skip through the constants here because there are just some signs that we don't really care about. The crucial point is that the Bethe wave function here, the exact wave function of this system here, is given by a superposition of plane waves. Okay? So these plane waves we will write in the following way. So there's -1 to the sign of the permutation that we have. And then there's a free part, which is summation over j, of the quasi-momentum of the particles here, which is represented in the linear case simply by this rapidity lambda. So essentially you just have lambda pj xj. Okay. But then there's another extra term here, which is e to the I over 2, summation, again use the same notations. Greater than or equal to 1, j2, of some scattering phase shifts that occur. So essentially there's a sign here of the coordinates. And then there's a scattering phase shift which depends on the rapidity differences. Okay, and this scattering phase shift here, phi of lambda, is by definition twice the arctan of lambda divided by the interaction. Okay, so I will actually let you verify that this is an exact eigenstate. Essentially, you will remember what happens in the case of the single impurity, so the single particle scattering with the single impurity. There's just a shift in the derivative of the wave function. Essentially, you can encode that in simply a phase difference between the two sides of the impurity. And this phase difference here depends essentially on the amplitude of the delta function, which is here just the value of the interaction parameter c. Okay, so here, each time two particles cross each other, they encounter a phase shift, e to the I phi, where this function here characterizes the size of this phase shift here. Okay, so I guess all of you who have done also the Bethe Ansatz for the spin chain will recognize this form here. So this form of the wave function here is completely universal to all integrable models. Okay, so that's what it's called the Bethe Ansatz anyway, as you know. So it has a number of important characteristics. Okay, so first of all, it's simply a combination of plane waves. The plane waves are combined together in this huge sum using relative amplitudes that are so chosen that the time-independent Schrödinger equation is solved. Okay? The language that we use to label the particles is that of these rapidities here. So essentially the rapidities are like the quantum numbers that specify which eigenstate we're talking about. And very importantly, the wave function has a fermionic-like structure hidden in it in the form of the summation over permutations. So this summation over permutations here shows you that if you take these sets of rapidities here in such a way that one of the pairs of rapidities coincide, then by definition, by construction, the wave function is 0. So that's like an exclusion principle that's applied to these wave functions. So this is very important because essentially it means that when you classify all the eigenstates of your theory, you use the language of free fermions. You will essentially introduce some quantum numbers that will be either filled or empty as labels for your wave functions. Yes?
So we constructed operators which commuted, not anti-commuted. So this should be bosonic.
Yes. So essentially this is what I did not write in here. In here, you can put essentially a phase that makes it. Yeah. So here there are two things, right? So the symmetry under permutation of the lambdas it's like an unphysical symmetry, if you want. It doesn't directly relate to anything physical. What's important is the symmetry with respect to exchange of the particle coordinates. When you exchange the coordinates, essentially, of course, because it's all bosonic statistics, it will give you a symmetric function. So if you look in the notes at equation 3.22, the little bit I didn't write, so this constant here, is actually a product of the signs of the coordinate differences with a product of the signs of the rapidity differences. The product of the signs of the coordinate differences is physical, okay? Because it's really just the bosonic statistics expressing itself. So then if you exchange two coordinates, you pick up a sign change from there, depending on which change you do. That can be reabsorbed in the others. The change of sign with the rapidities is conventional, okay? So when I do it, I use a completely symmetric function also of the rapidities. In the old literature, it's conventionally anti-symmetric, but that doesn't matter. Okay? Other questions? Okay, so like I said, I mean, this is really something completely standard. Those of you who have not derived or shown that this is the that this gives you eigenstates of neat vinegar, then you've got a wonderful evening ahead of you, following the notes and showing how it is. Okay. So let's just carry on a little bit, because of course here we have an example wave function, but this does not give us a basis of all our eigenstates. In order to obtain a basis of all our eigenstates, we introduce a kind of quantization scheme. That is, we will like to put our system in a finite size and just split the levels away from each other, and then just count them. So the way we do this is that we just put the system on a circle of circumference L. We just introduce some quantization protocol. Circle of circumference L. And we will impose some periodic boundary conditions on our wave functions. Essentially, that will tell us that the n-body wave function here, where we take one of the coordinates, say xj, and shift it by the circumference here, that this is just going to be the usual wave function, x1 up to xn. Okay? So you can do that for any of the j. And you can substitute these conditions into the form that we just wrote down for the beta wave function here. Do a little bit of reordering of the sums here. Right? And notice that it leads to a set of equations for the lambdas that are of this form. So this just tells you that e to the I lambda j times L has to be equal to a product of scattering matrices. So this is going to be equation 3.21, of which I will only write the most useful form, which is this one. So there's a product of L different than j of lambda j minus lambda L plus IC divided by lambda j minus lambda L minus IC. Okay, so the picture of this is extremely intuitive, because essentially you have your circle of length L, and you take your particles to be in, for example, various positions, and then you take one of the particles and you move it all the way around the circle, right up until you come to here. And then, of course, two things happen. So you need to operate with the translation operator over the whole length of the system. That essentially is represented by the left-hand side here. And each time you hit one of the other particles, you pick up a scattering phase shift corresponding to the scattering phase shift function that we had below. Right? So essentially, these scattering phase shifts, they're just these arctans. You remember the rule, arctan of x is 1 over 2i log of 1 plus ix divided by 1 minus ix. And then you can just rewrite it this way. Okay, so this is in the notes. Now, these are extremely important equations that you are already familiar with. These are just the famous Bethe equations for Lieb-Liniger, derived in 1963, as you all know. Essentially, they are extremely important because they give you very, very non-trivial constraints on the allowable rapidities that your wave functions can realize. Okay? So, I guess most of you have seen Bethe equations before, you've discussed them before, you will discuss them again in some other of these lectures anyway. We will discuss them quite extensively for various cases as we go along. But the idea is that these Bethe equations are typically extremely non-trivial to solve. Certainly if you have a finite system with a finite number of particles, finite length, finite value of the interaction, you cannot solve them in closed form. Okay? These are by nature transcendental equations here. In the case of spin chains, very often they become simple algebraic equations, but still solving them is rather complicated. There are situations where you can offer some analytical solutions to them, typically when you go to the thermodynamic limit and consider the ground state or simple excitations around these things. There are plenty of examples of that in the notes. But in general, these equations, you can't do much with them. One of the things that you can do, of course, is just solve them numerically. Okay? So in the fourth lecture, I'll show you how to compute correlation functions of these things, but these computations for correlation functions are for systems with a large but finite number of particles, say 200 particles or something like that. Yes?
I suspect you've been mathematically reversely proven, but it's not exactly so.
Well, that's so. In the case of Lieb-Liniger, I think it's almost automatic because of the exponential, right? So you would.
No, I understand that it looks terrible, but I mean,
yeah.
Still,
Yeah. In a sense, I don't know of any theorem, a kind of no-go theorem that's making sure that in all circumstances they would not be analytically solved. I can give you many, many specific cases of spin chains, the spin chain eigenstates, where the solution can be found analytically. But this will be for very particular values of the anisotropy, very particular states with, say, a mirror symmetry or something like that. But in general, yeah. However, in the case of spin chains, really it's just a high-order algebraic equation in the end that carries all the solutions. So it's difficult in general. Of course, analytical solutions to these things would be most welcome. Okay? So if you have these equations here, you're still not using a very economical language here, because essentially there are many, many solutions to these equations that need to be found, but the labeling is not very, very useful. So essentially a much more useful form is to take logs, and in this case you get the equations which are completely equivalent, but are written like this: so lambda j plus 1 over L summation L n of, well, let me write it explicitly, phase shift lambda j minus lambda L is equal to 2 pi over L times some integer or half integer ij. Okay, so ij here is chosen in the half odd integers for n even, and just in the integers for n odd. Okay, so the way you recognize this is completely immediate, because this is just like a quantization condition for free fermions that you would have. Essentially, the first term is just momentum, if you want. Second term for free particles would be absent, and then you just enclose your boundary conditions. The momenta get quantized by multiples of 2 pi over L. Okay? So here the only difference is that, of course, there are these phase shifts occurring in there. Okay? So this is the form of the Bethe equations that actually allows you to build up the catalog of your eigenstates in the language of eigenstates of free fermions. Okay? So there are various things, there are various properties of these equations here. So if you look at the sets of quantum numbers, there's a property that if you take two quantum numbers and put them equal, then the rapidities corresponding to these two quantum numbers will become equal. This is completely trivial to prove because the left-hand side of this equation is monotonic in lambda. Okay? So therefore, coinciding quantum numbers means coinciding rapidities, and the inverse statement is true. We've seen that coinciding rapidities do not lead to bona fide eigenstates. So essentially, we already have our first principle of classification. Acceptable eigenstates are characterized by sets of non-coincident integers. Okay, so you have to give me these quantum numbers. For an n-particle state, you give me n of them. And with these n quantum numbers, I have to solve for my rapidities via these equations to describe the actual wave function. Okay? There's another property in the case of the repulsive gas for C greater than 0, that all the solutions of these equations are in terms of real rapidities lambda. Okay? So all states in there are essentially scattering states. There are no bound states in the repulsive Lieb-Liniger. In fact, if you go back to the original paper of Lieb and Liniger, they briefly mention that for the case of the attractive gas, so C less than 0, very strange things happen. In fact, the attractive Lieb-Liniger is not thermodynamically stable. It has a ground state energy, which goes like minus some coefficient times the number of particles to the power of 3. Okay, it becomes a more and more bound state of all particles. Okay, so that was neglected for many, many years. But actually, these days there's still a lot of interest in the attractive gas because it is realizable experimentally. Okay, so that's why we looked at that a little bit, but I will not discuss the attractive gas at all in any of those lectures. If you want to hear about it, you can ask me in private. Okay, so that's the second property that's important here. All solutions of these Bethe equations for the repulsive gas are in terms of real rapidities lambda. Okay? If you have essentially a solution to these equations, so given a set of non-coincident quantum numbers, you get an eigenstate with energy E is equal to summation over all j of lambda j squared, and momentum P is equal to summation over j of lambda j. Okay? I think this is essentially the kind of very bare essentials of the classification scheme for eigenstates. Okay? So in particular, the ground state of n particles is given by the choice ij, so the set of quantum numbers, is n-1 over 2 up to n-1 over 2. Okay, so very often notes and things, I just draw this as this Fermi C-like of occupied quantum numbers. Okay, so you would imagine a number of available quantum numbers represented by these circles, and then you would choose to fill some of them. In this case here, you have a 6-particle ground state, so this would be 0 here. So the allowable quantum numbers, if you've got an even number of particles, they're half-odd integers, so 1/2, 3/2, 5/2, etc. So this would now be the ground state of 6 particles. Okay? It's the lowest energy state that you can construct from these things. Okay? Again, you can convince yourself quite easily that this is the ground state because any other choice of quantum numbers will lead to just a positive correction to the energy, as you can derive straight from the Bethe equations, taking the difference in the energies between these two states. Okay? So are you used to thinking of beta eigenstates in terms of these quantum numbers here? I guess for many of you it's kind of maybe not usual. But you will all have studied the Fermi gas in 1D, a gas of free fermions, and this is exactly what you would do here. This would be just a gas of fermions with periodic boundary conditions. Yes?
This can be rigorously proven that this is true.
Yes. Yeah. There's kind of, I think, a pseudo proof in the lead paper, and I think later on Douglas relooked at these issues with more care. But for this case here, it's relatively straightforward to see just by taking differences of the coming from the beta equations. For the spin chains, it's more complicated to prove as the ground state. But then there are papers from Xi and Yang. It's actually, I think it's in the first of the series of papers by Xi and Yang in 1966 that proves for the spin chain that it's that is the ground state. And actually, the Lieb-Liniger can be considered as a limit of one of these cases. In a sense, you could also take Young's proof and just generate it with the Lieb-Liniger case, and that would work. Yes?
Yeah, in scattering phase, was it a smooth function?
Yeah, it's just the arctan. So the notation that I use is that the scattering phase itself, so phi, is just 2 arctan of lambda over c. So it's really, really completely smooth over the whole real line, right? It's just going to have this shape here, right? With the limits just on plus or minus pi. So be careful, because in the literature, of course, there's a whole zoology of notations for these scattering phases here. Very often, the one that is used is the one that has a discontinuity at 0 in order to have different asymptotics. But this one is just the continuous one. And then if you want to translate from one notation to the other, it's a bit of a pain because you need to shift the quantum numbers. So in my case here, the quantum numbers are so chosen that you would construct them precisely as you would a gas of free fermion with no energy. So say you just do fermions with a k-squared dispersion relation, just on the continuum, you would construct your ground state like this. If you adopt the other convention for the scattering phase shift, where you essentially just put the discontinuity at 0, then all the quantum numbers are like shifted to one side. Okay? But this is just like pure convention. Everything can be equivalent. Okay? So now there's one statement which I often like to make concerning the Bethe Ansatz itself. The Bethe Ansatz, the form of the wave function here, has, in a first approximation, never been used to derive anything useful. Okay? It is manifestly a wave function. It is great. You can show that, all eigenstates take this form, which is truly remarkable. However, to do practical calculations with these wave functions is essentially a challenge beyond anybody's, capabilities. Why? Because just look at the wave function itself. It has a factorially large number of terms being summed over. All these terms here have essentially discontinuities at points of coinciding rapidities. So if I ask you to calculate anything in that, let's say that I ask you in a gas of interacting bosons like this, what is the correlation between having an atom here and an atom here? What you would like to do is take this wave function, apply an operator somewhere, apply another operator somewhere else, and then calculate the overlap with the wave function. But this would mean that you have 2 factorially large summations here. Each of the term is a 2n integral. And although you could do it term by term, you would never be able to resum these things here. Okay? Because it's just beyond any capabilities. So there are extremely few practical results that were derived with the actual form of the beta wave function. Okay? I can really count them on one hand. It's the advent of the algebraic Bethe Ansatz that made many of the calculations possible. So although it's all very beautiful, the only thing that we can easily do with Bethe Ansatz at first is to compute energy levels, i.e. to classify the set of states that we have. But answering any questions about the properties of these wave functions is an extremely non-trivial matter. Okay, so what we do at first is that we focus on energetics only. Okay, so we've discussed the ground state here. Essentially, there's one little kind of hint of a result that's given to you in the notes in section 3.4. It's about the norms of these beta wave functions. But maybe I'll just leave discussions of that later on for the third session. Okay, so maybe to rush you through, you see it's just great, right? We've talked for like 44 minutes and we've done 3 chapters already. So, is it kind of going too fast? Are you confident that you can catch up with the notes? Or would you rather me just really do the variations? No, it's okay? Okay.
One question.
Yes?
Could you remind all these integers I and j have to be discrete or not necessarily?
Yes. Yes. So let's maybe construct a few eigenstates. Okay. So let's just see how we do. So this is our ground state. So let me in fact do that here again. Let's rewrite our ground state in this way. Okay, and this is going to be my 0. So what does that give me? So these are the actual quantum numbers, the i's. Okay, so this one is 1/2, etc. Now, the statement is that every single eigenstate of the Linear is a Bethe Ansatz eigenstate. So where are the others? Essentially, this is a theory in the continuum, right? There is no UV cutoff. There's no maximal momentum, so the set of possible quantum numbers, it extends to infinity on either side. Okay, so really, when you draw the available quantum numbers, this extends to infinity on either side. So how do we construct excitations? Let us construct simple excitations by essentially, first of all, preserving the number of particles. Well, let me construct an excited state with 6 particles, then I choose the same quantum numbers here, but I'm now going to hop this guy here, like this. Okay? So this excitation here is a particle hole excitation because I've just created this hole here, this particle here. I could carry on and construct a whole family of excitations where I take this particle further and further and further out. Okay, so I can imagine just carrying on like this. And the whole stays here. And now I move this particle further and further out. Okay, let's say that. So this is called the type 1 excitation. I wish Lieb had chosen a more exciting term than type 1 for this excitation, but he called it type 1. Okay, so you just have your ground state, and then you take one of the particles here and you just let it disperse out. So this excitation, of course, has positive energy. You can plot its dispersion relation, in fact. So maybe I'm kind of almost getting ahead here. Let me mention that now and then come back. Okay, so type 1 is taking a particle out of the Fermi sea and letting it disperse out, giving it more and more and more energy. Of course, here there's another type of excitation that you can have. The other type of excitation is to consider taking the hole here and pushing it deeper and deeper in. Okay, so you could imagine having another form of excitation where now my hole has done one step in. a type 2. Okay? So what happens when I take the type 1 excitation and I give it higher and higher and higher momentum, it obtains infinite energy. If I give it infinite momentum, it will have positive infinite energy. Okay? It will have a kind of k-squared asymptote at very, very large momentum. But if I take my hole and I push it in, essentially what will happen is that the hole will represent an excitation with maximal energy as it reaches the middle of the Fermi sea, and then the energy will decrease again until I hit the other edge of the Fermi sea. Okay? So these, if you want, are the two fundamental excitations of Lieb-Liniger. And if I may just jump, if you look at the plots at the end of, so just after equation 428, and then just at the end of chapter 4, you have various plots. Let me show them to you on the screen here so you have them. Okay, so I don't know if you can see it well. So these lines here are the energies of states where I've created such a type 1 mode and I've given it higher and higher momentum. Okay, it's the energy versus momentum relationship, so the dispersion relation of type 1 modes. Okay? And then you can just look at the equivalent type 2 dispersion relation. So here what I'm doing is that I take the hole and I push it in further and further inside the sea until I reach the other side. Okay, so then the dispersion relation has this form almost of an inverted parabola, not quite, okay, where you just give it higher and higher energy and momentum until you reach the middle of the sea, and then you fall back down towards the edge. Okay, so with these two fundamental excitations, you can essentially construct a very complicated excited state if you want, by just populating more and more and more of these particle hole excitations into your original state. Yes?
Does this mean we can shift the place of the zero as we want and then still have the same energy?
So
if you're pushing the hole, it essentially means that you have now the place where the zero was in the beginning is slightly unsymmetric.
So there's like a Galilean boosted state. Okay, so if you want, in your classification of states, there are states that are identified with one another modulo a Galilean boost. Okay? So the hole crossing the Fermi sea means essentially once you reach the other side of the sea with your hole, you've obtained the state which is simply the boosted state. All particles have obtained 2 pi over L shift in their rapidities lambda. Okay, so then depending on what problem you're considering, you can either build that in straight or just still consider them as separate eigenstates. So in this case here, there is Galilean invariance. There is no equivalent to that in the case of spin chains. So in spin chains, when you cross the sea like this with your hole, you just you get a solution of the Bethe equations, which is not trivially relatable to the other one. In this case here, it's just a simple shift of all the lambdas that will give you the same state, the boosted state. Okay? So if you want, by solving one set of Bethe Ansatz equations for a particular choice of quantum numbers here, out of one solution of the Bethe equations, you can generate infinitely many by just doing this boost. Okay? If you want, you just have to solve the Bethe equations in the fundamental domain modulo these Galilean boosts. Okay?
Excuse me.
Yes?
You already took the thermodynamical limit here.
Yeah, so that's the thing that we did very quickly. You see, I was talking to you about the excitations here at finite size, so I could draw the quantum numbers. In the notes, I first do the thermodynamic limit, and then write the equations for the excitations of type 1, type 2 modes directly in the thermodynamic limit. Okay, so So let me now just spend a couple of minutes on the thermodynamic limit itself. Okay? The thermodynamic limit of integrable models, of course, is also kind of relatively uniformly implemented affair, whether you're talking about the thermodynamics of the Bose gas or the spin chains. The kind of basics are relatively similar. So let me just very briefly mention the most important equations that you need to know about this. So, okay, so when you look at the Bethe equations, the first thing that you see is that if you take a limit where you keep the filling per unit length of your theory to be finite, that is, you would scale L to infinity, but N to infinity so that the ratio N over L is finite, then the theory remains complicated. Of course, if you just take the limit L to infinity with N finite here, then it's completely trivial. Okay? So the interactions are only important at finite density. If you're at zero density, you can essentially just solve these equations straight. So at finite density, when you take the limit L to infinity, your rapidities lambda, they will essentially approach each other to order 1 over L. Okay, so you would imagine constructing an eigenstate with a finite energy density that is typically the distance between adjacent quantum numbers would be of order 1 and not thermodynamically large. In this case, the distance between the adjacent lambdas will scale like 1 over L. Right? So that allows you to replace the rapidities themselves with a function characterizing the distribution of rapidities on the real line. Okay? So this is all done for you in chapter 4 in rather explicit detail. Okay? So the idea, if I take a couple of minutes to do this. Okay, so here we just take L to infinity, N to infinity, and N over L finite. Okay, so lambda j plus 1 minus lambda j goes like 1 over L if ij plus 1 minus ij is of order 1. Okay? So what you can do is essentially consider instead of your set of rapidities lambda j, a distribution rho of lambda which is like this. Okay, so it's just a function which you write as a distribution which you will assume in the limit L goes to infinity becomes a smooth differentiable function of lambda, except perhaps at isolated points. Okay? Now, these distributions here, you see, become like the labels of your eigenstates. So I'd like 3 minutes to explain this to you, which is a bit of a challenge. Essentially, the notes thankfully will allow you to understand this. Let me just explain these things in a couple of minutes. Okay, so start from the Bethe equations themselves. Okay, so we had lambda j plus 1 over L sum over all the other rapidities, or even including all of them, doesn't matter because 5, 0, 0, lambda j minus lambda L is equal to 2 pi over, actually you have 2 pi times I j over L. So this little number here, you can just like rename xj. So x is now a coordinate in quantum number space. Okay, so if you want the quantum number space, which is coordinated by these allowable quantum numbers divided by L, and the limit L goes to infinity, just becomes the real line. Right? So in the limit L to infinity, I can imagine, so this is by definition 2 pi xj. Okay, now what I can say, well actually let me use this definition that I have here of the density, if you want. And since I've got delta functions here, what I can do is, you see, this summation here, really, I can replace it by an integral over the density. Okay, this summation here is like an integration over the density of these coordinates here. This is just a constant, it's just a continuous coordinate here. So what I can reinterpret this as, in the thermodynamic limit, is a function lambda which is coordinated by x plus now an integral minus infinity to infinity dy of phi of lambda of x minus lambda of y. Okay? Times the density rho of y. Okay? So I think that's one of the equations that I wrote for you in the notes, more or less. Okay? This is equal to 2 pi x. Now you see, we have an equation, we have an integral equation for a function lambda of x. But I can essentially view lambda as a function of x. This function will be invertible. I could also write x as a function of lambda. Question.
Is it the density of y or lambda of y?
So here, essentially, you have to see, so in this case here, I've written it directly in rapidity space. But what I can write, essentially, is this density here in quantum number space, where, let me just define it for you, where rho of x, so that is the function in the space of quantum numbers, is by definition just 1 over L. Now the summation over J of delta of x minus now the ij divided by L, or the xj. And then, because of the transformation rule of delta functions, I can just use straight it's an abusive notation. When I write rho of x, I mean the density in quantum number space. When I write rho of lambda, I mean it in rapidity space. Okay? But then you see, so now it's just a question of reinterpreting this equation here. Essentially, now what I'm saying is that instead of viewing lambda as a function of x, I will view x as a function of lambda. So the equation now becomes lambda plus integral d lambda prime of phi of lambda minus lambda prime rho of lambda prime is equal to 2 pi x of lambda. Okay? And now the trick, which again I will refer to the notes because it's best explained in there. So essentially, you see there in this notation here, I have my space of quantum numbers, and essentially my quantum numbers are either occupied or empty. So if you want, I have a density of occupied quantum numbers, and I have a density of holes. I have a density of occupied particles, and I have a density of occupied holes. But the total density is just 1. Right? Because my quantum numbers are either occupied or unoccupied. So there's a rho here, which corresponds to the particle density. Then there's the complementary density, which is the density of holes. And these two, in quantum number space, add up to 1. Okay? So essentially, you'll see in the notes, I will just refer to this because my time is already up. Okay, so I will just refer to this. denotes equations up to 4.9. Essentially what you get is an equation for these densities, right? Rho of lambda plus the rho whole of lambda is equal to some write it like this is the standard notation. So C is like a Cauchy kernel. I've defined it in one of the equations. Let me try to find which equation number it is. I can't find the number, the actual number, but it's just 1 over pi c divided by c squared plus lambda squared. Okay? And this sign here is just the convolution. Right? So this is a central equation. It's the thermodynamic form of the Bethe equations. So essentially it means that now in the continuum limit, in the thermodynamic limit, we label our eigenstates by a density function of these rapidities. Right? And each density function corresponds to an eigenstate, or to an ensemble of eigenstates in the thermodynamic limit. And conversely, every eigenstate has its density distribution, rho of lambda. Okay, so now with these densities, you can really play quite a lot of games about. So, for example, you can look at the shape of the ground state distributions, and then the excitations and things like that, and then do finite temperature thermodynamics. But maybe, in view of the time, I have to stop. What I will say is that next time I will do that, I will discuss the ground state and the thermodynamic limit, a little bit the finite temperature thermodynamics, and then we'll move immediately to spin chains. Okay? So, any questions? Please read the notes. Hopefully the notes will enlighten you if you've been completely or partially lost.
I have this question.
Yes.
Suppose you want to go to more than one dimension.
So what goes wrong? So why cannot we write the Bethe Ansatz in more than one dimension? So of course the great thing about one dimension is that the ordering in the wave function itself is completely explicit. If I write down my wave function by acting with creation operators in a basis where I label my sites, essentially, then there is a well-defined ordering. So when I change the ordering of the particles, essentially I necessarily scatter. And I know that the number of different reorderings that I have coincides with the number of scatterings that I need to go from one to the other. However, if I try to do the same thing in 2 dimensions, then I fail to make this correspondence between the reorderings and the number of scatterings, if you want. Because I can very well take 2 particles and change their positions without scattering them. So essentially, there's one thing that you have to understand. It is possible to write integrable models in higher dimensions. There is nothing more easy than that. I can write for you a 10-dimensional integrable model if you so wish. Okay? However, it will not be a model with local interactions. Okay? The very simple way to convince you that it's possible to write a higher dimensional problem is, okay, well, let me just write a spin chain and let me wrap it up on a certain lattice. Okay? But you see then, it's too simple in a sense, because I would have my interactions running only along certain rungs, not among the others. So that wouldn't work. Okay? I could just do the same thing with Lieb-Linegar, where I just go multiple times around an infinite number of things. I do a Pinot curve. I do a Lieb-Linegar on a Pinot curve. There you go. We've got a 2-dimensional integrable model, but it is not local. It's not local because its dynamics will be efficient one way, turned off the other way. Right?
So it's going to come to 4-dimensional integrable.
Yeah. No, of course, yeah.
But it's very hidden. It's very extremely hidden.
Yeah.
It's not included in space-time.
Yeah. Yeah, so you wouldn't kind of see the Bethe Ansatz appearing in higher dimensional things. But there are higher dimensional equivalents to Yang-Baxter relations and things. So once again, it's just a model of everything. But for example, so there's a model in the very beginning of the notes. I give you a list of models that are interesting for condensed matter. So one of them is the set of central spin models or Godin magnets. So these are really zero-dimensional models, or dimension ill-defined model. So they can correspond to a three-dimensional model. Because so the Godin magnets, they are such that essentially one of the elements interacts with all the others. So, but it's a discrete set of states. So if you want, it's like having a quantum dot. It's like having a ball in an arbitrary dimensional space with energy levels that are split and denumerable. And it doesn't matter whether it's a two-dimensional dot or a three-dimensional or a four-dimensional dot, provided you have discrete levels, then you can write an integrable model on it. So one-dimensionality is not a kind of requirement of Bethe Ansatz in this sense, in this strict sense. Kondo. So Kondo is, of course, a one-dimensional model, but representing a three-dimensional system, right? So you might not be familiar with it. It's essentially, Kondo model is just a model of a magnetic impurity interacting with gas and electrons. And then it becomes a one-dimensional model for the very simple reason that you take your three-dimensional electronic wave functions and you do a spherical harmonic expansion around the impurity. And of course, only the S-wave component interacts with the impurity. So you toss away all the other things, and then the only component of the wave function that you have is the radial dependence of the S-wave. Right? But then if you have two Kondo impurities, you cannot do that. Right? Because you would have to choose one point as the origin of your spherical coordinates, and then the second impurity would have much more than just the S-wave. But this is, Kondo lattice problem is unsolved in condensed matter.